This is Module 10, Lesson 1. We have talked about charges that are point charges, that are just a single, solitary, non-moving thing. Now it's time to look at charges that move. When we have charges that move, we have electricity, so it's time to start talking about current. So what current is basically just moving electrons or a flow of electrons. Remember that we said as far as we're concerned, we're going to look at charge as just being from the standpoint of gain or loss of electrons. So same thing goes with current. We're simply looking at the idea of a moving current. So the number of charges that flow by in a given second is what you call current. The unit of current is the ampere or amps. So if we write this as a number, we would write 4 with a capital A, and that would be read as 4 amps. You can say amperes, but why would you say that when you can just say amps? As far as your Canvas questions go, when you're doing quizzes and tests, you could put in the capital A, the amps, or the amperes, either way. I prefer to do less. Less is more, so A or amps is good for me. Now, as far as flowing current goes, you need to think about a couple of things that you probably know, but current can't flow unless there's a complete path. That's called a circuit. It has to have a complete way to go. It's kind of like the flow of water. If you have a blockage in a pipe, then you can't have a flow of water because there's nowhere for it to go to. You also have to have a potential difference. Potential difference is the fancy word for voltage. It's kind of like the same thing with water. If you have something that is completely flat, it's not completely flat, but as close as I could get it. So if we have a completely flat line and you have a completely level area, then water doesn't flow, it just stands still. But if you have a slope, then water can obviously run downhill because it has somewhere to go. That is the potential difference that we are talking about. It has to have like an area that's uphill and an area that's downhill in order for it to be able to get there. So some examples of voltage sources of potential differences that we use every day, of course, would be batteries and outlets. You use both of these a lot. Think about every time you charge your cell phone. Here's a couple of other things that deal with electricity that we need to think about. First is voltage. That's what we just said is the potential difference. The units of voltage are volts. Now this is where I think it gets a little bit confusing with our equations. We have current from the previous slide. The letter for current that is represented in a formula is the letter I. I stands for current, but yet the unit is A. So we have V for voltage in equations, and it's measured in units of V. We have R for resistance. Resistance is simply, I didn't put it on here, it's resistance to flow. It's how resistant the material is to the moving current that is going through it. So we'll put resistance to flow of electricity is what resistance is. The more resistance that you have, the harder it is for electron to flow through the substance, and the more likely you are to get unwanted results like heat or fire. The unit of resistance is called ohms. That's how we're going to say it, ohms. The letter that is used as the unit is the Greek letter omega. So if you saw 4 and then the omega symbol, you read that as 4 ohms. When you go to put this into Canvas, you're going to have to type out the word ohms. That's how I'm going to grade the quizzes and the tests, is you must type out ohms, O-H-M-S. I don't have a way for you to put the omega in there that I'm aware of or easily, so you're just going to have to put ohms. Now, since we have all 3 of those things, they can be related together. What we know about circuits is this. We know that the voltage or the potential difference of a circuit is equal to its current times its resistance. This is what we were just working on the previous slides. V is voltage, I is current, and that's an I, it's just not in block font with the Times New Roman type thing, the sans serif with the bars over the top and bottom. And then R is resistance. Their units are listed for you right here, volts, amps, and ohms. What can we do with that? Well, of course, we can work some equations. We can work some problems. So here's your first example problem that is on your paper for you. it says you have an electric fan with a resistance of 12 ohms. So as soon as I see the omega and it says resistance, we know that this is R. It requires 0.75 amps of current. So this is I for current. And it wants to know what voltage is required to operate the fan. So we're looking for V. Well, we have our formula. It's the only one we have so far that fits. V is equal to IR. Our voltage is going to be equal to 12 times 0.75. Now, I'll put those out of order according to this, but we all know that that doesn't matter. 12 times 0.75 is 9. Now we need to look at sig figs. This has 2 sig figs, and this has 2 sig figs, so I'm going to have to add a 0.0 to my answer to make it count as far as sig figs goes. And the answer is 9 volts. It would take 9 volts to make that fan work properly. Okay. Here's another one. Given a voltage of 120 volts and a current of 6 amps, what is the resistance? Well, how are we going to do this? This is our volts right there. It says V. I put the V for the voltage. And we have, of course, 6 amps. We know that amps measures current. So right here, this is I, and it wants to know R. Well, again, we have one formula to put this in right now. So we've got V is equal to IR, very simple. Let's set it up. We have 120 volts, and then we're going to have a current of 6 times our R. Solve for R, we get 20. Well, let's look at sig figs. This has 2. This has 2. This is going to have 2. So what we're going to have to do to make this proper is put the decimal on the end of it, 20 decimal. And you would need to do this in Canvas when you put in your quiz and your test answers, just put the decimal on the end of it. And then you draw the omega symbol, okay? 20 ohms is how it would be read. So now we need to talk about power. Power, in this sense, is basically how much electricity is being used by a device, like your alarm clock or your cell phone as it's charging, or your cell phone in general as it just works. It's often confused with voltage or energy, but this is just simply the rate at which electricity is turned into other forms of energy, like charging your battery, turning it into chemical energy, or like moving the blades of a fan inside of a motor. When you get your power bill, we're talking about this type of power. We're talking about electric power, okay? We could derive this using Ohm's law, but we're not going to work through that process. We're going to trust that they're just given here for us. On your reference table, this is actually given as one long equation like this. And that's perfectly fine. I've just separated it down here on the bottom into 3 separate equations. You are not going to work all of these together. You are simply going to solve for power using either this first set, the second one, or the third one. Now, as you can see, down at the bottom I have all of the units. Power is still measured in watts, just like it was before. In a previous unit, we solved for power by doing work divided by time, and our unit of power was also watts. It still is here. Now keep in mind this is a capital W. It would be 1 watt or multiple watts if it was plural, more than one. This is still a capital V and a capital A, and this is still your omega symbol for ohms. Now in Canvas, you're just going to have to type in the word ohms in place of putting the omega. So we can use these to solve for any of the variables that are given, and how I've been asking you to label your problems or annotate them as you go is how you're going to figure out which one of these that you want to use. So let's see what we could do with it. Well, here we have an electric heater that emits 100 watts when it's connected to a 120 volt power line. We know that watts measures power, so what it gave me was P. And when it's connected to 120 volts, we know that this measures voltage, because I see it's in volts. Volts is voltage. What is the resistance? It wants R. So how am I going to solve this? I'm going to go and I'm going to look at my equations, and I'm going to see I've got VI. That doesn't help me here. I don't have V. Well, I do have V, but I don't have I. I could do I squared R. I've got the P, but I don't have the I again. And then we have V squared over R. Hey, I have both of those. I have V and I have R. So we're going to go with P is equal to V squared over R. This is 100. I'm just going to move my decimal to the end. That looks easier to write. 1.00 times 10 to the second is 100. It's done this way to show significance. So we have 100 is equal to 120 squared over R. Now, we're going to solve for R. And what you're going to get for R is 140. Now, let's talk about sig figs. This has 3, and this has 2. And I don't have it, I could do it in my calculator real fast to see. I can't remember. I think it does come out to be an even 140. It should, but that'll be, no, maybe not. No, it actually comes out to be 144 in your calculator. But in terms of significance, this has 3 and this has 2. That's why we have to cut it down to 140. We have to lop off this 4. Now, what's the unit of resistance? Ohms. There we go, 140 ohms. The resistance of the heater is 140 ohms. Now, think about this. That's a pretty high number in terms of resistance. And would that make sense? Yes, because you want high resistance in objects that make heat because that's how the heat is going to be made. Because that amount of resistance creates the heat that's needed. If your resistance was lower, it wouldn't make any heat. It'd be a problem. Here's one more. We have a heater using 15 amps, that's I, connected to a 120 volt outlet. I keep using this because if you don't know, this is what you have in your house is 120 volts. Most other places have 240, but in the US we have 120. How much power does it use? So we're hunting P. Well, this time I see I and I see V. So P is equal to IV or VI. That's what we're going to do. We have 15 times 120. So 15 times 120, we get 1,800 watts. Now let's look at significance. This has 3 sig figs and this has 4. So this is going to have 3 sig figs. Now, the easiest way to do that with a pencil or a pen is to put the line over the 0 that you want to be significant. The 1 and the 8 are already significant. That's 3 sig figs. But in Canvas, you can't do that. So in Canvas, you really wouldn't have any choice but to put this in scientific notation to indicate that that 0 is significant. And remember, in Canvas, with scientific notation, you can just do this, like 1.8 E3, the E comes from your calculator if you choose to do it that way. Or you can type it out like this. All right? Now, we have one more thing, and that is electrical energy. So this is what your power bill actually tells you. You use power, but it's measured in terms of electrical energy. You also have this equation on your reference table. It is given for you just as I have it up here. It is big E with a sub E. Now, why do we have that? Because that lets you know that we are talking about electrical energy. And that's exactly what your reference table says, is electrical energy. And I did not fill that in down here for whatever reason. So here we go. This is electrical energy in my chicken scratch. This is, of course, our good friend power. And that little t we have seen many times before is time. Now, power, we said, is in watts. And the time often is in seconds. But usually here, this time is usually given in hours. And you can do watts or kilowatts as far as this goes. Depending on how you do, it's going to change your electrical energy answer. Probably the most preferred way to do it would be to use kilowatt hours because that's what your power bill uses. So in terms of electrical energy, it would be measured then in kilowatt hours if you're using kilowatts down here. Now, if you put in watts, you get watt hours, but that's just, it's a little less common. Kilowatt hours is the most common. All we're doing is we're multiplying the amount of power used times the time that it was used. So here's an example. We have an appliance with a current of 15 amps, so that's I, and it uses 120 volts of electricity. So that's letter V for our formulas. How much power does it use? Well, first of all, That's working the power problem. P is equal to IV. We have the 15 times 120. And what we got was 144, if you remember from the previous problem. Now, in terms of answering that question, 140 watts is what it uses. How much power does the appliance use in 2.3 hours? Well, that's working this one. As soon as it throws the time in there, and it really should say, I really should rephrase that. I think I did on your papers. How much electrical energy, or how much energy does the appliance use in 2.3 hours? We've got power times time. Now, since this is a two-part question, I want to make sure that I use my non-rounded power here. I'm going to use the 144, and we're going to multiply that by the 2.3 hours. And if I answer it this way, I'm going to get 331.2, but this was in watts. That would be watt hours. My preference would be that we switch that to kilowatt hours. You can switch it now by moving your decimal over 3 spaces, and then that would be kilowatt hours, or you could do it here, which would be turning this into 0.144 kilowatts instead of watts. You're still going to get the same answer over here. But now we need to look at sig figs. I can still only have 2. So that would be 0.33 kilowatt hours. Now, why am I insisting that we do kilowatt hours? This is a Canvas thing. Because I can't put this in both ways. I can only put it in so that it grades different options. Like I could put both of these numbers in so that it would accept either 331.2 or 0.3312. Like a flavor of those. Or I can put in that the units that it'll count watt hours or kilowatt hours, but then that would allow you to mix and match. So if you said 0.33 watt hours, that's wrong. It's 0.33 kilowatt hours. And the only way that I can tie them together is just to limit the answer choices. So I want you to use kilowatt hours. It's just going to have to be the way we operate in order to be on the same page. So these are pretty simple equations. I don't anticipate you having a lot of difficulty with this. The main difficulty might be with sig figs and remembering to do kilowatt hours for the electrical energy questions. It's time for you to practice. If you have questions, then please let me know. I'll be available during office hours, or you can send me a message.